Example 5, angle of depression this time. Very similar to angle of elevation, but it's looking down this time. All right. Top of a cliff is 85 meters above sea level. Min saw a tall ship. He estimated the angle of depression was 17 degrees. Okay, let's have a look. First thing you're going to have to do is you're going to draw a diagram. So I'm going to get a little bit fancy here. I'm going to say that there is a top of a cliff, which is 85 meters above sea level. There's the sea. And I'll just do the top of the cliff. There you go. There's the cliff. And here's our mate Min standing up on top of the cliff. Okay, so you get a bit of an idea of what's going on. He saw a tall ship. Well, I won't do it in blue because you never see it. Let's do it in purple. So he saw a tall ship. There's my ship. That'll do. And he estimated that the angle of depression was 17 degrees. So what we're looking at here is, I'm going to go from the top of the cliff, is that he's looking at that angle there, but his angle of depression, remember, is always from the horizontal. So there's that 17 degrees. It's not down here. It is that 17 degrees in there. Okay, so that's the angle of depression. It always goes from the horizontal. All right, what we're trying to work out is how far it is from the base of the cliff. So we know that height, and we're trying to find that value there. So we'll call that x. All right. How do we do that? At the moment, we've got an angle that is not inside our triangle. But we should remember from year 7 and 8 that if you've got two lines that are parallel and they're cut by a transversal, then this angle in here is equal to this angle here because they are alternate angles. Okay, so that means we've got our 17 degrees there. That means that that angle there is also 17 degrees. And that's good. We like being able to do that because all of a sudden we have our theta, we have our opposite, and we have our adjacent. Oh, yes, that's correct. Got it right. Okay, so now what we want to do is then just decide, okay, which one are we using? Well, we've got opposite and adjacent, so we're going to use tan theta equals opposite over adjacent. In this case, theta is 17 degrees. Our opposite equals 85, and our adjacent is x. So we go tan of 17 equals 85 over x. Rearrange that. X tan 17 equals 85. So x equals 85 over tan 17. Chuck that into the calculator. 85 over tan 17. Close the bracket. Hit equals 278. Oops, scroll up a bit. So x equals 278. Wants to the nearest meter, so we've got 0.022, so it would be 278 meters. So that's question A done. We've got the distance there, 278 meters. The next question, B, says how far is the ship in the straight line from the top of the cliff? So in other words, it's trying to find this length here, which for us is our hypotenuse. So this time we've got our opposite and we've got our hypotenuse. We've still got our angle. So let's use sine theta equals opposite over hypotenuse. In this case, theta is still 17 degrees. Our opposite is 85 and our hypotenuse is unknown. So we're going to do exactly the same process. So sine 17 equals 85 over x, which is x sine 17 equals 85. So x equals 85 over sine 17. So exactly the same as the previous one, except we're using the sine ratio now because we're finding a different side. So we've got 85 over sine of 17, close my bracket, hit equals, and we get 290.725, blah, 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 and it wants us to the nearest meter as well, which equals 291 meters. Now, a good way to just double check and make sure you had done the ratios correctly, it doesn't give you exact answers, but you can just check. We just found the hypotenuse. We found the longest side. So therefore, it should be longer than the previous answer. So we got 291 in the second part, 278 in the first one. So we're pretty much golden. Okay, done.